All right, good morning, everybody. So in the last lecture, we were talking about inheritance, and we had started to implement a subclass of counter that represents a counter that stops when you get to integer max value instead of wrapping around back to 0. And so we got to the constructors of the class, and we came to this slide here, and there's these 3 rules here that you're supposed to follow whenever you create a class in Java. Not just a subclass, but whenever you create a class in Java. And I was about to explain to you why these rules are required in the Java language. Before I do that, let's quickly go back and look at the implementation of stopping counter so far. Right, so we have a class called stopping counter. It's going to be a subclass of counters so that we can reuse the features of the counter class, right? So we don't have to re-implement them. So we want to extend the counter class, right? So the keyword extends is used to indicate that you have an inheritance relationship. The counter is the superclass, and your new class is the subclass. Okay. And we have our constructors here. So here's our stopping counter constructor, which sets the value of the counter to 0, and we have the stopping counter constructor that sets the value to that value there. Right. So when you're implementing the constructors, you have to follow the 3 rules. Right. So rule number 1 is on the first line of a constructor, you must call another constructor. So on line 14 and on line 23, we have to call another constructor. Right? On this line here, we're calling another stopping counter constructor. So we're calling the second constructor, passing in 0 for the value of the counter. In the second constructor, we're calling the superclass constructor. So now we're calling the counter constructor, passing in the value to the counter constructor, And if you go and look at the counter class, right, its constructor that, where'd it go? Counter, here, is technically incorrect. I should really validate the value. So something like that. And so the counter constructor validates the incoming value. If it's not negative, it goes ahead and sets the value of the counter to 0. Okay, so notice in the counter class, in the stopping counter class, there are no fields, right? The only field we need to implement the stopping counter is a field for the value, and we already have that field. We inherited it from the counter class, right? So that field there is now protected. If the field is protected, that means the subclasses inherit the field and can see the field directly by name. Okay, and so there are other ways to implement these constructors, right? And so the way that I'm showing you here is the way that strictly follows the rules on the previous slide, right? There are many ways you can do this, though. So you could also write the following, super like that, right? So in the no argument constructor, we can call the superclass no argument constructor. Right, so that super round bracket calls the counter no argument constructor, which sets the value to 0. Right, so that would be fine too. You could also write the following. Right, so we inherit the field value, so we have access to it here. So you could also write that, and that's fine. You might say, hey, what happened to rule number 1? You're supposed to call a constructor on the first line. You have to remember that there is another rule that's not shown on the slide. Well, sorry, it is on the slide. It's in one of the subpoints. It says that if you don't call the superclass constructor, if you don't call another constructor, then Java inserts a call to the superclass constructor, superclass no argument constructor for you. Right, so if you write that, then what the compiler does is it silently inserts this for you. Right? And that explains why we never have to call. We never called a superclass constructor in any of our previous classes, right? Because the compiler is inserting that call for you. Right? And if the compiler is inserting that call for you, you could also do something similar in the second constructor. Right? So for example, you could write so that's also fine. Right? You should remember here, though, that a counter's value is not allowed to be negative, so you really need to validate the value coming in here as well, right? So So you really should do that as well. And once you realize that, it makes sense, it should hopefully make sense to you that it's easier now to call the superclass constructor, right? Because the superclass constructor does everything you need it to do, right? It does the validation and it sets the value, this dot value to value, right? So this is legal, but it's much easier to simply write that, right? And yet another way to do this is you could call the superclass constructor, the no argument constructor, right? Then validate, right? And then write this value equals value, right? Which is dumb, right? The superclass constructor sets value to 0, right? Then you're going to validate the value, and then you're going to reassign this value to value. So this is probably not a great way to do it. And there's probably other ways you could do this as well, right? But I think that gets the point across. All right, so why do we need these rules? So that's the topic of this, that's the start of this lecture. So the next set of lecture slides actually picks up from this slide here. So I'm just going to jump to the next set of lecture slides. Right, so the slides overlap. All right, so why are the rules needed? So to understand why the rules are needed, you need to understand what exactly is a subclass. So a subclass looks like a new class, right? It has the same public interface that the superclass has, right? All the public methods that are in the superclass, the subclass also has. Right? The subclass is allowed to add extra methods and fields if it needs to. Right? Okay, so in inheritance in Java, when you use inheritance, it does more than just copy the interface of the superclass. Right? What actually happens is your subclass object actually contains a subobject of the parent class type. What does that mean? It means every stopping counter has a counter object inside of it. Right? If an object has so whenever you have an object in Java, that object needs to be initialized, right? It needs to be constructed, just like any other object. Right? So the subobject, so the counterpart of the stopping counter, needs to be initialized. Right? How do you initialize any object in Java? You call a constructor. Right? And so that's why the call to the constructor is required. So what happened, right? So why is a call to the superclass constructor needed? Right? Because every stopping counter is a counter, right? That's what inheritance means, right? And the counterpart of stopping counter needs to be initialized, right? In a picture, this is what happens when you make a stopping counter. This is backwards, sorry. I have to fix this slide. I've got these backwards. This is actually a pretty serious error. So, okay, so I'm going to make a new stopping counter, right, whose value starts at 1. Right, so what happens when you do this? So new allocates memory for a stopping counter object somewhere, right? So the red block is just the chunk of memory that our stopping counter is going to occupy. Right? So new runs makes that. New calls the constructor to fill in the fields of a stopping counter. Right? So what does the stopping counter constructor do? Right? The very first line of the stopping counter constructor is a call to another constructor. Right? And in fact, it's a call to the counter constructor. Right? So that initializes the counterpart of the stopping counter. Right? So the counter constructor now starts running. What does the counter constructor do? On its very first line is a call to its superclass constructor, right? So it calls the object constructor, right, to initialize the object part of the counter. So the object constructor now runs, right? I don't know what it does, right? It does something, and then it finishes, right? When it completes, the object part of our stopping counter has now been fully initialized. So when the object counter finishes running, the counter constructor can now continue running, right? So on the so what does the counter constructor do? It sets it validates the 1, right? If the 1 is not negative, it goes ahead and sets this value to 1, right? So notice that the value field lives inside the counter object. right? It lives inside the, it lives inside the superclass counter object. Right? When it sets the value, the counter constructor is now done running. Right? And so that means the stopping counter constructor can now finish running. Right? The stopping counter constructor doesn't do anything, right? The only line in the stopping counter constructor is the call to the counter constructor. And so the stopping counter is now completely initialized. Right? And so notice the order in which things are initialized in, right? So when you make the stopping counter, it's the object part of the counter that gets built first, right? That's followed by the counter part of the object, right? And only when the counter part of the object is finished being constructed can stopping counter finish constructing, can the stopping counter constructor finish initializing the stopping counter part, the stopping counter object. Right? So the objects are built from the inside out. Right? And so in order to build the objects from the inside out, right, you need to call the superclass constructor on the first line of all your constructors. Right? That's the only way that you can do this. To construct the objects from the inside out. Okay, any questions there? All right. The obvious question is why do you have to build the counter from the inside out? Right? So why do I have to initialize this part first, and then the counter part, and then the stopping counter part? Right? And the answer is because the stopping counter constructor might need to do something with that field value. So in this example, it doesn't, right? But you can come up with examples where the stopping counter wants to use that field as part of the initialization, right? And so there might be a second field that relies on that value to initialize the second field, right? If you don't initialize this value first, you can't initialize, stopping counter can't correctly initialize its second field, right? And so the objects have to be built from the inside out, right? There's so that's why the rules are set up the way they are. Okay, so we're now finally, we can finish up implementing stopping counter, right? So we now have to change how advance works because advance in the counter class wraps around to 0. We want to stop at integer max value, so now we override advance, right? It's easy to override advance, right? If the value is not integer max value, go ahead and add 1, right? If it is integer max value, do nothing, and the counter doesn't go anywhere. Right? And you're finally done, right? So you've completed the implementation of your stopping counter class. Okay, so one more example. So instead of stopping at max value, what happens if we want to indicate some sort of error, right? So in other words, what happens if we would like to throw an exception when you get to max value? It turns out this is not a great idea. We'll talk about, we might revisit this discussion when we talk about post conditions later on, but we can go ahead and do this for the time being. Right? Okay, so you make another class, right? So now I'm going to make a counter called throwing counter. This counter throws an exception when it hits integer max value. Right? We're going to extend counter because we want to reuse the code that we have in counter. Right? Again, there's no fields. Right? We don't need another field to keep track of the value of our throwing counter. Right? We already have a field that we inherited from counter. Right? Go ahead and implement your constructors because you never inherit a constructor. Right? So that constructor there needs to set the value of the counter to 0. Easiest way to do this, well, the easiest way to do this is just to call the superclass no argument constructor. Right? So super round bracket would be fine here. Right. Second constructor initializes the counter, throwing counter's value to that. So call the superclass constructor, pass in the value. What about advance? So advance needs to throw an exception when you hit integer max value. So if you're not at integer max value, go ahead and add 1. Right? Otherwise, throw an exception. So here I throw a runtime exception. You might choose to throw some other kind of exception here. Right? And that's it. Right? So the mechanics of implementing inheritance is straightforward if you remember the rules about constructors. Right? Typically, all you do is, well, it's not typically. So if you want to, you can add extra fields to your class. Right? Keep in mind you are inheriting fields from the superclass. Right? Anything that's not private or package private, you inherit. So anything that's public or protected, you inherit. right? And you reuse those and you don't redeclare those fields. Right? Any methods that you need to change the behavior of, you simply override. Right? All the other methods you don't touch, right? You don't re-implement them, and you just reuse them as they stand. Right? And of course, you have to add your own constructors because you never, classes never inherit constructors from their superclass. Okay. So in this example here, we've used inheritance to implement a bunch of counters that behave differently when the counter gets advanced to past its maximum value. Right? So using inheritance, we create separate classes that all they do is override advance. Right? There's a different way to implement this. There is a different approach to solve this problem. Right? So if you want counters that behave differently when they hit advance, you don't have to use inheritance. Right? There's another way to do this. So the alternative approach is to realize, in this particular case, it's only advance that's changing each time. Right? So stopping counter, advance stops. Throwing counter, advance throws an exception. And in a regular counter, the advance just rolls around back to 0. Right? And so you can take that behavior, right, and then, oops, sorry, go away, and encapsulate that behavior in another object. So what the heck do I mean about that? So this is what I mean. Okay, so I've got this class called alt counter, which is just our original counter class, right? So it's the original counter class whose value is private. So we're not going to use inheritance in this case, right? I'm going to modify this class slightly. Right? I'm going to add another field called strategy. So this is of type advanced strategy. So I'm going to explain what this does in just a second. Right? Our strategy object is going to be the object that knows what to do when advance is called. Right? So in other words, in advance, right, I'm not going to put in all the logic needed to advance the counter. Right? Instead, I'm going to rely on our strategy object to figure out what is the next value given the current value. Right? So our strategy object has a method called next. Right? Next takes in the current value of the counter, and it computes the new value of the counter. Right? So how the heck does this work? Right? So what does our strategy object look like? Right? So notice its type is advanced strategy. So you go look at advanced strategy, right? And it's an interface. Right? So the interface has only one method in it called next. Right? What does next do? It tells you the next value of the counter given its current value. Right? So how does this help us? You can now create classes that implement advanced strategy. Right? So for example, if you want the counter to wrap around to 0, right, you create a wrap strategy class. Right? It implements our interface. Right? So in implementing the interface, it needs to provide a next method. Right? So what does next do? Well, if the current value is max value, I want the next value to be 0. Right? If the current value is not max value, I simply want to add 1 to the current value. Right? And if you look at that code, it's almost the exact same code that was in the original counter advance method. Right? All I've done is I've moved it into an object somewhere. Right? For a stopping counter, right, you create a stopping strategy. Right? It implements our advanced strategy interface, so it needs to provide a method next. Right? So if the current value is integer max value, we want the counter to stop. So the next value is just integer max value. Right? If it's not integer max value, we want to add 1 to the counter. So we return counter current plus 1. Right? And I didn't do the throwing strategy. But for the throwing strategy, it would be if current equals integer max value, throw some exception. Right? Otherwise, return current plus 1. Now, in our alt counter class, right, all we do is provide a way for the user to set the strategy of the counter. Right? And so that constructor there sets the value to 0, and it sets the strategy to the wrapping strategy, so it behaves like our original counter. Right? This constructor here sets the value to 0, and it lets the caller specify what kind of strategy they want to use. Right? Do they want a stopping counter? Do they want a wrapping counter? Do they want a throwing counter? Right? So they can just make their own advanced strategy object and pass in that object. In advance, where did advance go? Oops. Sorry. Right. And so in advance, right, advance simply relies on the strategy object to figure out what is the next value for the counter. Right. And so there is an alternative way to create a family of counter. There's an alternative way to provide a counter class where in this case, the user gets to specify how the counter behaves when it hits integer max value. Here. Okay. So what I just showed you is an example of what's called the strategy design pattern. Okay. So design patterns are frequently occurring patterns in software. Right? And so these were first described, when were they first described? Sometime in the 80s or 90s. I don't remember exactly when. I don't know if any course at Queen's specifically teaches you about this stuff. But there's a famous book called Design Patterns, written by 4 authors. Colloquially, they're called the Gang of 4. So if you search for all these terms, you will find them on the internet. And so they wrote this book called Elements of Reusable Object-Oriented Software, I guess in 1994. And this book has been quite influential in object-oriented programming. One of the patterns they described is this thing called strategy. And there's the UML class diagram for strategy. Right? And so to read this diagram, you can almost read this diagram at this point in the course. So you have some class here called the context, and it has some method called operation. So in our example, this is the counter class, and operation is its advanced method. Right? You want the advanced method to change its behavior based on some strategy. Right? So there's our interface strategy. Right? In our case, it's called advanced strategy. Right? And our interface defines some method that our counter class is going to use. Right? And so here it's just called algorithm. In our case, it's just next. Right? We have 2 different classes. We've got our wrapping strategy, right? That implements the method the interface says it must implement. Right? So our wrapping strategy implements the next method. Right? And our stopping strategy also implements the next method. Right? The way that the operation is implemented is it simply uses its strategy object to calculate what needs to be done. Right? And so in our case, our advanced method uses our strategy object to determine what is the next value of the counter. This arrow here, that's an example of a one-way aggregation. Right? So, sorry, one-way association. Right? And so previously I told you an association is shown as a solid line. Right? Here it's shown as a solid line with a little arrow on it. And so this is an association that is strictly one way. Right? So every alt counter has a advanced strategy object, but the opposite is not true. Right? This arrow here is optional, but it's here in this diagram, so I thought I'd explain to you what's going on. This picture down here, right? So remember the open arrow with a solid line connecting 2 classes shows you inheritance. Here, that's an interface. So strictly speaking, this is an inheritance, right? This is classes implementing the interface. So when you have that situation, you use a dashed line instead of a solid line. Right? So there's an example of a design pattern that you can use. Well, there's an example of a design pattern, right? And this is all stuff that's not really covered in this course. I don't know where else it might be covered in 2nd or 3rd year or 4th year. I'm not sure if there is a course that talks about this stuff specifically at Queen's. But if you're interested in them, you can come talk to me more about them, or you can go find that book. All right, so let's carry on. Any questions so far? Super. What happens if you want to compare counters for equality? Right? So remember in our counter class, we implemented equals. Right? Equals for a counter is returns true if the 2 counters have the same value. Right? Now that we have a hierarchy of classes, does equals still work correctly? Right? And the answer is currently no. So where's our counter class? Okay, so I did change this already. So let me put this back to what we know equals to be. Right, so just to remind you, how does equals work? Right, so I showed you one way of implementing equals. Right, so remember in equals, so one of the requirements of equals is that an object is equal to itself. Right, the way to express that in the equals method is to check if this equals obj, right, where obj is the argument to the method. Right. The second requirement of equals is that equals never throws an exception if obj is null, and it always returns false. Right. So previously we would write if obj equals null, return false. Right. Requirement number 3 was two objects can be equal if and only if they have the exact same type, and that should right away raise some flags, red flags for you. Right. So to implement that, we used getClass. Right. So if the classes of the two objects are different, they can't be equal, so we return false. Right. If we get past the third if statement, we know that obj is a counter, so I can cast obj to a counter, right, and store it in the variable other. Right. Now I can access the value of the other counter. Right, and now we can compare the two values, and if they're equal, we can return true, otherwise we return false. Right. In inheritance, that line there is a problem. Sorry. Sorry, my keyboard is not really working properly. There we go. That line there is a problem. Right. So why is that line there a problem? So imagine you have a counter object C, right, and you have a stopping counter object S. Right, you now write C equals S. Right? If they have the same value, equals still returns false. Right? Why do they return false? Because this getClass returns the class corresponding to counter, and obj getClass returns the class corresponding to stopping counter. They're not equal. So they return false, even if your two counters have the same value. So this version of equals doesn't work if you need to compare subclasses for equality. Okay, so what do you have to do here? So instead, you need to use the second version of equals, which I skipped over previously. So now I have to go back and tell you what the second version of equals looks like. And so that means I have to go to, not there. I need to go back to lecture slide set 16. This is the set where this is the set of lecture slides where I told you about hash code. So the beginning of that set of lecture slides was equals using this thing called instance of. And so now is an appropriate time to go back and look at these slides. So the previous version of equals I told you about is correct if you don't care about inheritance. Right? Now that we care about inheritance, we have a problem. Right. Okay, so the previous, we still have the same requirements. Right? An instance is always equal to itself. Right? An instance is never equal to null. Furthermore, we never throw an exception if null is the argument to equals. Right? Now, instead of objects having the exact same type or equal, we want objects with compatible types to be equal. Right? Where compatible means they are related by inheritance. Right? Finally, we want objects with the same state to be equal. Right? So for an object to be, an object is always equal to itself, right? That's the exact same thing as before. Right? Requirement number 2, x equals null, it always returns false, right? And we never throw an exception, right? So before we would explicitly test if obj is null. Today we don't have to, because the next thing we're going to do does that test for us, right? And so that's step 3, right? So now we want objects whose types are compatible to possibly be equal, right? So in other words, if they're related by inheritance, we would like them to be, we want to be able to test if they're equal. Right? And so for that, we need the instance of operator. Right? So instance of is an operator even though it looks like, even though it's spelled out in letters, right? So it's not a symbol of some kind, it's still an operator in Java. Right? So the way you use instance of is you pass it in a reference of some kind, right? So a variable. Right? And on the right-hand side, you specify some type, right? Some reference type, so a class type or an interface type. Right? And this thing here returns true or false. Right? So what it does is it tests if that thing there is an instance of that thing there. Right? So if that variable is, sorry, if the object referred to by this variable has that class type, then instance of returns true. Right? If that variable implements that interface type, then instance of returns true. Right? If that variable there is a subclass of that type there, instance of also returns true. Right? So here, instance of tests if a reference refers to an object that implements a specified interface. Right? Is an instance of that type, right? Or is a subclass of that type. Right? If the reference is null, so if you pass in, if you use a variable whose value is null, instance of automatically returns false. So you never have to worry about it throwing an exception. So when you're working in inheritance, right? Oh wait, this is completely botched too. Sorry, I have to go back and fix this slide too. OBJ. Right. So now in inheritance, we want to know, right? Is that thing coming in, right? I don't care. Is it just a point two? This is for the point two class, right? I don't care. Is this a point two object, right? But rather, I now care. Is it a point two object or is it a subclass of point two? Right. If it is, then I know that OBJ has an x and a y coordinate. Right. So I can compare the coordinates of our 2 points now. Right. So if OBJ is not a point two object or a subclass of point two, right, now we can return false. Right. And now the rest of equals is exactly the same. Right. And so the rest of equals, right, once you get past, oh, it's still broken. OBJ. Okay, so if we get to this point here, we know that OBJ is in fact some kind of point two object, right? It's either a point two object or it's a subclass of point two. Right? So I'm allowed to cast OBJ to a point two object, right, and store that in other. And now I can access the x and y coordinates of other and compare them. Right? So the only difference between the two versions of equals is the use of instance of instead of get class. Right? You need to use the instance of version of equals if you want to compare subclasses for equality. Right? And so let's see how this works within our counter hierarchy now. Okay, so in the counter class, right, so remember in the superclass, right, I'm going to change equals so that it does not use get class. Oh wait, this actually explains what's going on. I'm going to change it to the following, right? I'm going to change it to the instance of version of equals. Okay, so let's see what happens if we use the old version of equals, so the get class version of equals. Right? So here I have a counter C1 and C2, right? Their values are both 0 because we use the no argument constructor. Right? What happens when we call equals with C1 and C2? Right? So C1's a counter, right? C2 is a counter, right? Do they have the same type, right? Is get class return the same class for both counters? The answer is yes, right? So this part here, we get past this if statement here, right? Get class returns the same for C1 and C2, so we can go to here and now we can compare the two values. What happens if we have two stopping counters? So C3 and C4 are both stopping counter objects, right? Their values are both 0. We have not overridden equals in stopping counter, so we inherit the version we get from counter. This get class returns stopping counter for C3, right? OBJ get class returns stopping counter for C4, right? They're the same, so we skip over the if statement and come down to here, right? And now we compare their values. Their values are both 0, so equals returns true. And this looks like everything is working just fine. Right? So the problem is what happens when you change one of the two counter types. Right? So here C1 is counter, and here C2 on the right-hand side, it says it's a stopping counter. So now when you run equals, right, remember C1 is a counter, C2 is actually a stopping counter. Right? So this get class returns counter for C1, obj get class returns stopping counter for C2. Right? They are not equal, so now equals returns false, even though the two counters' values are 0. Right? And the same is true down here. Right? If the two counters have different types, equals will return false because the get class version of equals says the two objects don't have the same type. Right? We would like these comparisons to work. Right? There's nothing different about these counters other than that they behave differently when you get to max value. Right? So we'd like to be able to compare all these counters by their value. So here we have to use the instance of version of equals. Right? Now when you use the instance of version of equals, right, if we have two counters who are that have the same type, right, obj has counter, his type is counter, right? Is counter an instance of counter? The answer is yes, right? Counter is the same class as counter, right? So now we skip past the if statement and come down here, right? When we have two stopping counters, whoops, sorry, too far. Okay, when we have two stopping counters, is a stopping counter an instance of counter? Well, stopping counter is a subclass of counter, so instance of returns true. Right? Not true is false, so we skip over the if statement and come down to here. Right? And so this also works. Right? When you have counter and stopping counter, right, we're going to look at the type of C2, so that's stopping counter in this case. Right? Is a stopping counter an instance of counter? The answer is yes. So again, we skip past the if statement and come down to here, and now we can compare their values. Right? Notice the cast works here. The cast is fine. Right? You can always cast a subclass to one of its ancestor types. Right? So you can cast a stopping counter to a counter. Right? You can also cast a stopping counter to an object if you need to. In this case, we don't need to. Right? But you can cast up the inheritance hierarchy. Right? And if we have stopping counter and throwing counter, C3 equals C4. So the only thing that matters is the type of C4 here. Right? So C4 is a throwing counter. So is a throwing counter an instance of counter? Well, throwing counter is a subclass of counter, so that's true. So again, jump down to here, compare their two values, and if the values are the same, they're equal. Right? So using instance of, you now have a version of equals that works in an inheritance hierarchy. Right? Notice that there's an important point here that's not emphasized on the slides. Right? The important part here is that counter is the class that defines equals. Right? So the superclass defines equals. The subclasses do not override equals. Right? And if you want to see what happens if the subclasses decide to override equals, go ahead and try it, and then see if you can compare subclass objects to one another. The answer is it's not going to work. So you have to stop equals at the superclass. Right? You cannot override. There's usually no good way to override equals in the subclasses and have have subclass comparisons work out. Okay. And so all of this now leads to the following point. So there should be, some of you might be confused as to why we can do some of these things here. Right? So there's a few confusing things in these slides. Right? So I have a stopping counter object on the right-hand side. Why can I store that in a counter variable? Right? Back here, right? If you pass in a stopping counter, why can I cast the stopping counter to a counter object? Right? And so this leads into the discussion of what's called polymorphism. And so the question here is, if you have an object, a reference, or an object, how many types does it actually have? Right? And so in Java, unless you have a big O object, all objects have more than one type. Right? And so the types of an object include whatever class it is. Right? So a point2 is a point2 object. It also includes all of its ancestor class types, right? So a point2 object is also a big O object because it inherits from object, right? And if your class implements any interfaces, all of those interfaces are also, the types of the object also include all of the interfaces that it implements. Right? So here's point2. This is our most recent version of point2. Right? Point2 extends object even though we never said it did. Right? And it also implements comparable. So the types of point2 are point2. Right? Its superclasses, or all of its ancestor classes, so that's object, and all of its interfaces, so comparable point2. Right, so every point2 object actually has 3 types. Right, stopping counter extends counter. Right, don't forget counter extends object, so stopping counter also extends object. Right, and we've implemented comparable. I guess we assume counter implements comparable. So every stopping counter has 4 types. Right, stopping counter, its direct superclass. Right, whatever superclasses counter has, so that's object. And whatever interfaces have been implemented, and so that's comparable. Right? So every stopping counter has 4 types. String extends object and implements 3 interfaces. So string has 5 types, right? String itself, its superclass type, and all of its interface types. And so every object in Java has more than 1 type, unless you have a big O object. Right? And so in object-oriented programming, this is known as polymorphism. Right? And so the dictionary definition of polymorphism is the condition of occurring in several different forms. Right? Java has what's called subtype polymorphism. Right? Every object in Java has more than 1 type. Right? The subtypes are substitutable for their ancestor types. So when you use a variable C, whose type is counter, right, we say that this type here, right, is called the declared type. Right? So it's the type that's used to declare the variable C. Right? So using C, right, what can you store in it? Well, you can always store null, because null means no object. Right? So C equals null means C refers to no object. Right? It should be obvious that you can store a counter reference in C, right? So C equals new counter, right? But you can also store a reference to any descendant type of counter, right? So you can write C equals new stopping counter, and the reason you can do that is because every stopping counter, one of its types is big C counter. So the declared type here, so right, the variable, the type that you say the variable is, right? That also applies to a field or parameter, right? The declared type determines what methods can you call using that variable. All right, so here, OBJ. What is the declared type of OBJ? Well, it's big O object, right? You don't care what's on the right-hand side for the time being, right? For the declared type, you're looking at the left-hand side of the assignment operator, right? So the declared type of OBJ is big O object, right? So using OBJ, right? What methods can I call? Well, I can certainly call any method that belongs to big O object. So I can call toString, right? The class object defines the method toString, so we can definitely use OBJ to call toString. The mistake that's often made by programmers new to object-oriented languages is that they try to use the type on the right-hand side. They try to call a method belonging to the type on the right-hand side when using OBJ. Right? So you might say, hey, OBJ is really an array list, and I know that every list has an add method. Right? So why don't I try to use OBJ to add the string hello to my list, right? And so in Java, that's an error, right? You cannot use OBJ to call the list method, right? Why? Because the declared type is the type that determines what methods can be used to call the object. Right? So here, what you've told the compiler is you said, hey, obj is a big O object. Right? And that's all that the compiler cares about when you use obj. Right? It's the same issue that occurs in equals. Right? So when you say that in equals, right, your parameter obj, its type is big O object, right? You're telling the compiler obj is a big O object, right? In equals, you eventually want to get the actual type of obj, right? And so in this case, I want to get the counterpart of obj, right? And so that's why the cast is needed down here, right? You can't write this value equals obj value, right? Even though you know obj is in fact a counter object, right? You first have to tell the compiler, hey, obj is in fact a counter object, right? So ignore what I said up here, right? Now, trust me, obj is a counter object, and now you can go ahead and use other to get the value. Right? So declared type determines what you can do with the variable. Right? Here's another example. So here I've got a set T, right? So I've said that T is a set. Right? On the right-hand side, I said that T refers to a tree set. Right? So can I use T to call add? And the answer is yes, right? Every set has an add method. Right? Tree set has a first method, right? So remember, tree sets are sorted sets. So the notion that there is a first element in a sorted set makes sense. Right? If you try to do that, it doesn't work. Right? Set does not have a first method. So you can't try to call first using the variable name T. Right. Okay, so when in the right-hand side of an assignment or initialization expression, right, the type on the right-hand side is called the runtime type or the actual type. Right, so when you write C equals new stopping counter, that thing there is the actual type or runtime type. So here, C, declared type is counter, right? Runtime type or actual type is stopping counter. Right? The runtime type determines what version of a method you get when you call when you call a method. Right? It's actually the what version of a non-static method you get. Right? So here, when I use when I use obj to call toString. Right? Step one, can I actually use obj to call toString? So the answer is yes, right? Big O object has a toString method, so this line works. Right? Now, what version of toString do I get? Right? I get the counter version of toString. Right? So the right-hand side, or the runtime type, determines which version of the method you get when the method actually runs. Right? Here, I get the counter version of toString. I don't get the object version of toString. Right. So if you remember, there was, this method print takes in a big O object reference. Right? How does print work? Well, it calls toString on obj to get the string representation of the object. Right? It's the runtime type of obj that determines which version of toString you get. Right? So for example, right, if I pass in a string and call print, right, I get the string version of toString. Right? So you get hi there. Right? If I pass in a list T, I get the array list version of toString when I call print. Right? And when I use a date object, right, I get the date version of toString. Right? Notice in the third example here, the declared type of O is big O object. Right? But the actual type of O is actually a date. Right? So even though I'm passing a big O object to print, right, when the toString method is actually called, right, it's the date version of toString that gets called. Okay. So observe here that the compiler cannot determine which version of toString gets called. Right? So go back here. Right? All the compiler sees in the printer class is this method print. Right? It sees obj.toString. Right? The compiler says, is there actually a toString method belonging to obj? Right? right? It goes and looks at what the declared type of OBJ is, and that's big O object, right? It looks in the object class and it says, oh yes, there is a toString method, this is legal, right? So the compiler happily compiles this code, right? It's not until you run this code that the actual version of toString that gets called is determined, right? So the actual version of toString that's called, you can't figure, no one knows what that's going to be until you actually run the code, right? So using the runtime type to determine which version of a method to call is called dynamic dispatch or late binding. They both mean the same thing in this context, right? So dynamic meaning at runtime, right? Dispatch meaning what version am I trying to call, right? Late binding means the same thing, right? So late means at runtime. Early means at compile time, right? Binding means what version of the method to call, right? So dynamic dispatch means what version of the method am I calling when I run the program, right? It's the runtime type that determines which version of the method is called. Oh, we're over time. So I guess we'll stop there and we'll continue the discussion tomorrow.